When we perform the two-slit experiment with light waves, we're going to notice an interference pattern on our screen over here. We're going to use the same wavelength through both slits. So we'll send it through, and what happens is we actually get a major interference pattern right here, just a huge bright spot. And then it starts to become a little bit dimmer and dimmer as we go up here. But I'm going to be more interested in this particular bright spot right here. And since that's a bright spot, I'm going to go ahead and try to maybe figure out the distance to that bright spot. I'll measure it straight in the middle here, because we've measured this straight in the middle. And I'll call this the Y bright here, because these are bright spots. Of course, in between here, these are all going to be darker fringes, darker spots. But we need to label these somehow. So we'll call this particular bright spot here in the middle M equals 0. And then this becomes M equals 1, this becomes M equals 2, and up here we get to the 1, 2, 3. This would be the third M. But everything starts on the M equals 0, so it's pretty important to remember that. Then we can come down here and reach to the negative 1s and stuff. We can keep going down if we want to. Well, if I'm particularly interested in this bright spot here, where M equals 3, then I'm going to draw a line from here to that spot, and I'll call this particular angle theta. And then what I can do is I can draw another line from here to here that's 90 degrees, and I'll call that particular angle also theta. What that allows me to do is basically calculate this little interesting segment here, which we'll call little d path difference. This is essentially how much more length has been traveled by this light wave than this light wave. So we can basically take out a ruler and measure this to be about 10 inches, this one to be about 8 inches, and then this little path difference here is actually just about 2 inches. Interesting. Let's try to describe the interference pattern we get here on the screen with some equations. First, we're going to define this theta in degrees, which is going to be this angle here. Now, at the moment, this angle is leading us towards this particular Y bright location here. So we're going to try to describe that, Y bright. And so we'll see that it's just equal to L tangent of a theta, that particular theta that we're using right now for the bright spot. Notice how tangent of that angle would just be opposite over adjacent, and that would just be Y over L. We can just move the L over and we can actually solve for the Y. Well, naturally we could perform the same trick with the Y dark, so let's just go ahead and do that as well. Say that Y dark is going to be equal to the L tangent, and we're going to change this theta to the specific Y dark that would be corresponding to this particular spot. It would be somewhere in between those two areas, something like right here. That would be your Y dark. Now, when this experiment was performed, then it was observed that the distances between these fringes here, whether it was the bright fringes or the dark fringes, that distance always remains the same. And it is proportional to the lambda, which is the wavelength, times the length between these two posts here, divided by the distance between these two slits. So from here, let's try to set this value equal to that. So we'll just go lambda L over the D. And then we'll say, okay, well, if we have an M equal to 0, then we actually get that Y bright is 0. If we set M equal to 1, we get that distance. If we set M equal to 3, we actually arrive at this distance. So this formula works. For the Y dark, we could do the same thing. So we'll just set lambda L over the D. And then we'll multiply that. But this time, let's realize that it's not going to be just the M's, but it's more like a 1/2. This is 1/2 here. So if we take our M, we're going to have to add a half. If we start with an M is 0 here, it actually ends us up here, and that's our first dark y location here. So these formulas actually work based off of our experimental evidence. Now let's try to calculate the path difference, which is going to be the distance that this light ray travels more than this light ray. And so we'll set the path difference here equal to, well, if we know this is theta, then we can actually use the sine, because that would be opposite over hypotenuse. So we'll just rearrange the equation a little bit, and we'll just put d here, and then we'll say sine of the theta bright that we're using. Let's set up the same equation for the destructive path differential. So we'll say that d is equal to the d times the sine of the theta dark. It's the same equation, but we're going to need a small adjustment. Now let's do a little quick trick. We know that for small angles, sine of theta is approximately equal to the tangent of theta. So let's substitute that sine of theta for the tangent of theta, which will be y over L, tangent of theta opposite over adjacent. And then this d over here, let's rearrange this equation. You're going to notice that you're going to get lambda, and then there's a L over y. Well, when you multiply those two things together, the L over the y and the y over the L are going to cancel. And the only thing you are left with is that lambda. So we just set these equal to lambda. Okay. Now, of course, it's going to change when you're thinking about this being 0 or 1 or 2 or 3. So we do set that up for the bright, and then also here for the dark we put plus 1/2 in order to describe these particular points. So that's how we can derive these particular equations here. Now it's important to understand the interference patterns that we get here in terms of the bright and the dark and the maximums and minimums. So if we draw some waves like that, we could see how here these points intersect, and that's kind of like, oh, well, that's going to be your maximum points right here. So these will be the brightest spots, bright. But then notice how far away these 2 points are, here and here, across. So that distance there is actually going to be your minimum, and this is where you get your dark fringes. If you're trying to describe the wave function of these light rays, then you're going to need the phase difference between them, so let's define that. It's going to be the phase difference is equal to 2 pi, and then we have our path differential, and then we'll divide that by the lambda. Now let's describe two slits with different wavelengths. So we'll send through S1, we'll send lambda 1, and then through S2, we'll send the lambda 2. And so we're going to get different patterns over here. And we're going to say, okay, well, for the red ones, we're going to get a pattern like this. And then we'll have maybe 4 different places where we have it show up. And then at the same time, for the blues, they would only get 3. Right? It's pretty large differences here, but then at some point they actually meet up again right here. So at the same time that this remember this is m equals 0 here, and this m equals 1, this m equals 2. At the same time that m equals 2, over here we actually get m equals 0 here, and then m equals 1, m equals 2, and m equals 3. So at that point those two m's are the same, but every other place they wouldn't match up. The zeros, of course, will always match up, but we can set these up in sort of like an equation. We could say that if we're looking to find the y red, and we kind of want to find when they intersect with the y blue, then we can just set lambda 1 m1 equal to the lambda 2 m2. Now that just comes from using this equation for both of them, and then since the L and D will cancel out on both sides, you're just left with the lambdas and then the 2 m values that you're looking for that are corresponding to those particular levels. Now when you look at the intensities of these particular bright spots, then you're going to notice that the intensity will be the highest in the center where m equals 0, highest Imax. And as you start to get higher m's, then the I will become lower, so the lower intensity. And over here, the intensity will become lower as well on the left as you get to negative m's. Now this is corresponding to the 2 slit, so we kind of have this broad wavelengths going across here. Once we reach the 3 slits, you'll notice that we get much thinner peaks here, and then we also get a little bit of rays over here as well, brightness here, and are not going to be as strong. And so we get kind of different types of interference patterns based off of the numbers of slits that we have, but these particular locations will remain the same, and in fact they'll actually become brighter and brighter here, but it still follows the same curvature. It's just interesting observations. Now once we get to the 4 slit here, we can notice that it gets a little sloppy, but these peaks will become very, very defined here, and of course it just follows the same pattern consistently. So from this conclusion, we could state that we get this sort of a little arc here, where these are the Imaxes. And we could say that the more slits that we have, that just gives us more intensity. Alright, we're going to try to describe the intensity on the screen, so we'll say that the I average over time is supposed to be equal to the I max, but notice how it starts to change intensities over here, so we'll use the cosine squared to get rid of the negatives. This is supposed to be for some sort of a radians value, but we're going to go ahead and put the pi, and then a d comes from this one over here, and then this is the sine of theta, and then let's make sure that this one is degrees, the theta, whereas the cosine squared portion here, this is supposed to be in radians, and we'll just divide this part by the wavelength. Now remember that for small angles, the sine of theta is approximately equal to tangent of theta, so we could use y over L. We could say that sine of theta is approximately y over L, and so you can actually use that in here to approximate this I average if you need to. Now let's discuss the thin film reflection or refraction. So we're going to have this setup here. We have a very thin film, and we have the same material maybe on both sides, but there's going to be a different end for the film. So this is going to act more like a speed bump here. So for the light rays, we're going to send one here, meaning like this, and you would want to reflect off here a little bit at the same angle, but then some of it would want to come down into this thin film, and then it will continue on its way here. So let's start this off with a phase angle of 0, and then when it gets reflected off, it'll have a phase of 180 degrees. We'll also label this particular lambda in here as lambda sub n, because it's going to be slightly different than the lambda that is going to be through here. Let's define that lambda sub n as being lambda divided by the n that's inside of here. Let's label these angles here as being a phase of 0, and so then we can see how this is just a one-phase reversal, because we only get one change of angle here. That would be this one. So this will also create an interference pattern, and we're going to notice that the second ray travels a distance of, well, 2t. So if we set up our fringe distance over here, the delta y, we can actually use that as well, but we'll just alter it slightly. So we'll go lambda L, divide that by 2t, because the distance that we have here is actually 2t. That's the extra distance that this thing traveled. Now let's try to calculate this 2t distance for constructive interference. We're going to claim that that's the bright, as in most reflective here. So we're going to say 2t is equal to m plus 1/2, and then we'll multiply that by this lambda over n. So that'll just give us our 2t. And we'll do the same thing for the destructive, which we'll call the least reflective. That'll give us the dark spots. So we'll just say 2t is equal to m times lambda here. And in both cases, the m is going to start at 0, which will give us the brightest possible spot, most intensity. Then we have 1, 2, etc. Now the two-phase reversal is going to act more like an airbag. So we're going to have sort of like air, and then a soft surface is going to protect you from slamming against that harder surface. And what I mean is increasing ends. So the idea is that sometimes these speed bumps will just be like, okay, this is just a slightly different end than on both sides. Or it could be that you're going from like a low end to maybe a high end over here, and then you come back down to like a low or medium end over here. But the idea is that this is just going to act as a speed bump, so you'll get one phase reversal. Imagine hitting into a rubber band versus hitting into a wall. That will reflect you back in different ways. Well, in this situation, we're actually hitting into that wall, and so we're going to get two-phase reversal. We'll see what that means. So we'll start by sending our light wave through here, and then of course it's going to want to come down into that, and then all of a sudden, bam, it's just going to kind of smack down into this wall over here. So that'll be the end of that. But again, we can label this as the lambda n, and this will be starting off at a theta of 0, and this will be reflected off here at a theta of 180, just as before. And the main difference is that once this gets reflected off of here and through here, this one also gets an angle of 180. That's how we can get our two phase reversals. We have one of them here and then one of them right here. Now it's important to note that when we go to the two phase reversal, we also have to switch these equations, and so we'll say that 2nt is going to be equal to m times lambda. And then for the destructive, we'll say that 2nt is equal to m plus a half times the lambda. And we stay consistent with our m's here. So it's just pretty important to understand when we use the difference between the two-phase reversal and the one-phase reversal, because the two-phase reversal will be sort of hitting into harder and harder ends. So higher and higher ends, the ends are increasing here. And then over here, we would get that we get a low end, a high end, and a low or medium end over here as well. Or just be the same material on both sides. But here's kind of more like a softer reflection, and over here it's more of like a harder. Just remember that for these two, you could also use the delta y, which will give you the fringe distances, and you can multiply it by the m's and try to figure out, how long those distances are. So that's pretty cool.